Start recording. All right, internet humans, welcome back to the health of the human. It's me, J. Logan K, and we're still learning about this state of GPT. We're just going to continue on with the press release that the Microsoft devs just dropped. We're going to put our playback speed at like 1.5, pop it up on full screen. And if our computer ever loads
straight from internet into sequences of integers, because that's the native representation over which GPTs function. Now, this is a lossless kind of translation between pieces of text and tokens and integers, and there are a number of algorithms for this state.
Come on, keep going.
Typically, for example, you could use something like byte-pair encoding, which iteratively merges little text chunks and groups them into with tokens. And so here I'm showing some example chunks of these tokens, and then this is the raw integer sequence that will actually feed into a transformer. Now, here I'm showing two sort of like examples for hyperparameters that govern this stage. So GPT-4, we did not release too much information about how it was trained with so long, so I'm using GPT-3's numbers, but GPT-3 is, of course, a little bit old by now, about 3 years ago. But Llama is a fairly recent model from Meta. So these are roughly the orders of magnitude that we're dealing with when we're doing pre-training. The vocabulary size is usually a couple 10,000 tokens. The context length is usually something like 2,000, 4,000, or nowadays even 100,000. And this governs the maximum number of integers that the GPT will look at when it's trying to predict the next integer in the sequence. You can see that roughly the number of parameters is, say, 65 billion for Llama. Now, even though Llama has only 65B parameters compared to GPT-3's 175 billion parameters, Llama is a significantly more powerful model. And intuitively, that's because the model is trained for significantly longer. In this case, 1.4 trillion tokens instead of just 300 billion tokens. So you shouldn't judge the power of the model just by the number of parameters that it contains.
So pretty much I think the big concept here is there's clever ways to increase the success and the usefulness of these large language models. And before there was like this debate of, well, if we tokenize every piece of written human like text, are we ever going to run out of tokens? Like, are we going to run out of things to put into our language models? And it seems like that's kind of a silly question. And it's really just, so training these models is starting to look like a lot like training humans. It's actually kind of neat. So the next like stage of like technologists are actually starting to be a lot more like preschool teachers, because you really have to it's kind of like having a baby savant. You got to work with it and train it how to be more useful.
We're showing some training hyperparameters. So for example, to train the 65B model, Meta used 2,000 GPUs, roughly 21 days of training, and roughly several $1 million. And so that's the rough orders of magnitude that you should have in mind for the pre-training stage. Now, when we're actually pre-training, what happens? Roughly speaking, we are going to take our tokens and we're going to lay them out into data batches. So we have these arrays that will feed into the transformer, and these arrays are B, the batch size, and these are all independent examples stack up in rows, and B by T, T being the maximum context length. So in my picture, I only have 10, the context length, so this would be 2,000, 4,000, etc. So these are extremely long rows. And what we do is we take these documents and we pack them into rows, and we delimit them with these special end-of-text tokens, basically from the transformer where a new document begins. And so here I have a few examples of documents, and then I stretch them out into this input. Now we're going to feed all of these numbers into transformer. And let me just focus on a single particular cell, but the same thing will happen at every cell in the diagram.
I'm confused.
The green cell is going to take a look at all of the tokens before it, so all the tokens in yellow, and we're going to feed that entire context into the transformer neural network. And the transformer is going to try to predict the next token in the sequence, in this case in red. Now the transformer, I don't have too much time to unfortunately go into the full details of this neural network architecture. It's just a large blob of neural net stuff for our purposes, and it's got several 10 billion parameters typically, or something like that. And of course, as you choose these parameters, you're getting different predictive distributions for every single one of these cells. And so, for example, if our vocabulary size is 50,257 tokens, then we're going to have that many numbers because we need to specify a probability distribution for what comes next. So basically, a probability for whatever may follow. Now, in this specific example, for the specific cell, 513 will come next. And so we can use this as a source of supervision to update our transformer weights. And so we're applying this basically on every single cell in parallel, and we keep swapping batches, and we're trying to get the transformer to make the correct predictions over what token comes next in the sequence. So let me show you more concretely what this looks like when you train one of these models. This is actually coming from a New York Times, and they trained a small GPT on Shakespeare. And so here's a small snippet of Shakespeare, and they trained a GPT on it. Now, in the beginning, at initialization, the GPT starts with completely random weights. So you're just getting completely random outputs as well. But over time, as you train the GPT longer and longer, you are getting more and more coherent and consistent samples from the model. And the way you sample from it, of course, is you predict what comes next. You sample from that distribution.
Okay, so this is actually kind of crazy, but it's sounding exactly the way you get good at something in like real life. Like the way that like athletes train is you have to continually repeat the same movements over and over again, iterations. And from looking right here, it seems like what it's saying is actually, look, after 250, it didn't really do it that well. After 500, it still didn't do it that well. 5,000 iterations, it started doing it better. And then 30,000. So it's crazy that, yeah, that learning is actually through trial and error. You just got to try things out and keep making little micro adjustments until you get something that's useful. And it's insane because these big large language models have the capability of like supercomputers, but they actually think the way humans do. And well, like a human can only do so much computation per second. It's not measurable to what computers do.
And you keep feeding that back into the process, and you can basically sample large sequences. And so by the end, you see that the transformer has learned
It's really great. It's a great time.
These are the kinds of possibilities. Now we're doing logically training. Effectively, we're looking at the loss function over time as you train, and low loss means that our transformer is predicting the correct, is getting a higher probability to be the correct next integer in the sequence. Now, what are we going to do with the model once we train it after? Well, the first thing that we noticed, the field, is that these models basically, in the process of language modeling, learn very powerful general representations, and it's possible to very efficiently fine-tune them for any arbitrary downstream task you might be interested in. So as an example, if you're interested in sentiment classification, the approach used to be that you collect a bunch of positives and negatives, and then you train some kind of an NLP model for that. But the new approach is do more sentiment classification, go off and do large language model pre-training, train a large transformer, and then you may only have a few examples, and you can very efficiently fine-tune your model for that task. And so this works very well in practice. And the reason for this is that basically the transformer is forced to multitask a huge amount of tasks in the language modeling task, because just in terms of predicting the next token, it's forced to understand a lot about the structure of the text and all the different concepts therein. So that was GPT-1. Now, around the time of GPT-2, people noticed that actually even better than fine-tuning, you can actually prompt these models very effectively.
Bro, that was only GPT-1?
Fake documents. So in this example, for example, we have some passage, and then we sort of want to do QA. This is called few-shot prompt. And then we do Q, and then as the transformer is trying to complete the document, it's actually answering our question. And so this is an example of prompt engineering a base model, making it believe that it's sort of imitating a document and getting it to perform a task. And so this kicked off, I think, the era of, I would say, prompting over fine-tuning, and seeing that this actually can work extremely well on a lot of problems, even without training any neural networks, fine-tuning, or so on. Now, since then, we've seen an entire evolutionary tree of base models that everyone has trained. Not all of these models are available. For example, the GPT-4 base model was never released. The GPT-4 model that you might be interacting with over API is not a base model. It's an assistant model, and we're going to cover how to get those in a bit. GPT-3 base model is available via API under the name DaVinci, and GPT-2 base model is available even as weights on our GitHub repo. But currently, the best available base model probably is the Llama series from Meta, although it is not commercially available.
Whoa, so that's really interesting. So if we go back to this thing, so right here is the tree of all the different models that are out here right now. This is actually really, really special. And if you look at it, they were saying that Llama, the meta model, is the best one out there right now, which would be this one, I think. Or maybe it's this main one in gray. This is the main one. And then you see up here that GPT-4, yeah, Llama's right below it. What's that say? Decoder only, encoder, decoder. Oh, okay, so there's different, like, types of ways to go about it. And it looks like the decoder only model is the one that's really popping off right here.
Available base model probably is the Llama series from Meta, although it is not commercially available. Out is base models are not assistants. They don't want to make answers to your questions. They just want to complete documents. So if you tell them, write a poem about the bread and cheese, it will just, it will answer questions with more questions. It's just completing what it thinks is a document. However, you can prompt them in a specific way for base models that is more likely to work. So as an example, here's a poem about bread and cheese, and in that case, it will autocomplete correctly. You can even trick base models into being assistants. And the way you would do this is you would create like a specific few-shot prompt that makes it look like there's some kind of a document between a human and assistant. For basically QA prompt response count data, and that is low quantity, high quality, some random field response. And when they write it all truthful and harmless, they're long and to some extent. Now you can actually continue the pipeline from. So what I'm going to do is we're now going to shift our data collection to be of the form of comparisons. So here's an example of what our data set will look like. I have the same prompt, identical prompt on the top, which is asking the assistant to write a program or function that checks if a given string is a palindrome. And then what we do is we take the
Yeah, do you know what palindromes are? It's like Anna, A-N-N-A, if it's the same four words and backwards.
Model, which we've already trained, and we create multiple completions. So in this case, we have 3 completions that the model has created. And then we ask people to rank these completions. So if you stare at this for a while, and by the way, these are very difficult things to do to compare some of these predictions, and this can take people even hours for a single prompt completion pairs. But let's say we decided that one piece is much better than the others, and so we rank them. Then we can follow that with something that looks very much kind of like a binary classification on all the possible pairs between these completions. So what we do now is we lay out our prompt in rows, and the prompt's identical across all 3 rows here. So it's all the same prompt, but the completion bits vary. And so the yellow tokens are coming from the SFT model. Then what we do is we append another special reward readout token at the end, and we basically only supervise the transformer at this single green token. And the transformer will predict some reward for how good that completion is for that prompt. And so basically it makes a guess about the quality of each completion. And then once it makes a guess for every one of them, we also have the ground truth, which is telling us the ranking of them. And so we can actually enforce that some of these numbers should be much higher than others. We formulate into a law, and we train our model to make reward predictions that are consistent with the ground truth coming from the comparisons from all these contractors.
This is insane! These nerds they're just using math to predict the word that's going to come next. Like, that's bonkers. We're making artificial sentience. Like, we're literally building artificial life. It's amazing. The internet's great right now. Anyway, that's it for this video. Remember, comment it, subscribe it, like it, get the algo. Like, who owns? Yeah, Google Alphabet. They have an AI algorithm, and it'd be cool if we can do good on that algorithm. So do the things, make this thing pop up, pop off. You know what to do. Anyway, subscribe. Stay tuned for the next one. If you missed part 1, you can, I don't even know, like, find it. I guess it's the internet. You can find anything. Anyway, part 3 coming soon. I bet it's already online now.